Okay. Bonjour à tous. Hello, everyone. George Gedenadis from Western University, Ariel Figov from Mathematics Knowledge Network, and Sarah Ganon from Brock University, as well as myself, Chantal Buteau from Brock University. We are pleased to welcome you back to the online seminar series on programming in mathematics education. We wish to begin by acknowledging this land where the Fields Institute for Research in Mathematical Sciences is situated, from where we are hosting this event. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to be hosting our online seminar series from this land. So today we are hearing the last seminar from the whole seminar series. It's been wonderful how different perspectives have been brought by our speakers about this area of programming or computational thinking in mathematics education, an area of growing interest in different parts of the world. And as it has been reflected in the registration of this seminar series, indeed, we have received more than 250 registration from 30 different countries. So we see that it's been an interest from different parts of the world. And also it's an interest from different stakeholders in mathematics education, and that's been also reflected in the registration. So we've had about a half of researchers, education researchers registering to this online seminar series, about a quarter of undergraduate, graduate students, education students, and also about a quarter of elementary and high school teachers and leaders. So in addition to all the seminars that have been presented, we are thankful to the speakers who have been recommending some resources, materials for teachers, and as well some related research papers that complementing to the seminars. This is all posted on our website of the seminar series, and in addition to the recording of all the seminars. This is for free of access. So we want to thank the Mathematics Knowledge Network, hosted at the Fields Institute for Research in Mathematical Sciences and the Social Sciences of Humanities Research Council of Canada, for the financial support of this event, so making it possible for so many people in different parts of the world to be participating in this event. So today, the schedule for the seminar will be similar to the previous one. My colleague George will first introduce the speaker. Then Dr. Drijvers will be presenting for about 45 minutes, which will be followed up by a session of about 25 minutes for questions and discussion. And then we will be ending this 2020 seminar series by a short closing at the end. And so on this, I believe we are ready to start. So please, George, if you please can introduce the speaker.
Thank you, Chantal. A pleasure to introduce today's speaker, Dr. Paul Drijvers. Paul Drijvers is a professor of mathematics education at Utrecht University in Utrecht, the Netherlands, and scientific director of the well-known Freudenthal Institute within the university's science faculty. His research interests include the role of digital technology in mathematics education, mathematical thinking, and embodiment in mathematics education. Amongst his most cited papers is an ESM contribution entitled The Teacher and the Tool on instrumental orchestration, and an item on realistic mathematics education co-authored by Professor Marja van der Hoover Penhuizen in the Encyclopedia of Mathematics Education. In his work on digital technology in mathematics education, Paul became interested in computational thinking, and he's currently leading a research project called Computational Thinking and Mathematical Thinking, Digital Literacy in Mathematics Curricula. With that, join me in welcoming Paul Drijvers for his presentation, Computational Thinking in the Mathematics Classroom.
Thank you very much, George. I will share my screen. Thank you very much for your kind introduction. Maya van den Heuvel-Panhuizen is a difficult name to pronounce, I admit, but you did very well. If you hear some noises, there's just a thunderstorm starting here, so you might see some flashes and hear some big noises. The title of the talk is Computational Thinking in the Mathematics Classroom, and I'm very happy, and it's an honor to be the final speaker in this very nice seminar series, and I would like to thank the organizers for setting this up. So this is the title, and well, if you allow me, I would just try to slightly change the title for today and to replace programming by computational thinking, which is a bit more of my topic, to be honest. As an outline, I would like to start with some snapshots from previous seminars, briefly discuss the question what computational thinking is, how it relates to mathematical thinking, and how it could be addressed in the mathematics classroom. In the meantime, I should say that I'm a bit, well, what should I say, concerned, because compared to the previous speakers, my experience with computational thinking is very limited. In fact, I have just one small ongoing project, so not decades of experience like some of the others. And as a second issue, I intended to show you a lot of student data, but which we were supposed to collect last spring, but due to the COVID school closed down, we were not able to do so. So as part of my expectation management, I would like to tell you that the student data are unfortunately lacking for the moment. And therefore the main points in the talk will be on points 3 and 4. So snapshots from previous seminars. I should admit that I missed the fourth one by Ricardo, so I cannot really speak about that. But if I look at the others, I will briefly show you my takeaways, so to say. Well, of course, it was a pleasure to hear Celia and Richard again. And what I remember from their talk is that they stress the overlap between computational and mathematical thinking, and that they highlight programming as being a fruitful way. For example, they provide evidence that, well, mathematical thinking can really be enhanced through programming, I would say. And to being a bit provocative, I would like to stress that, in my opinion, coding and programming is a means rather than a goal, at least from the perspective of mathematics education. That's why I took the liberty to slightly change the title. The next session was by Francis and Davis, and what I appreciated in their talk is that they provide a very interesting theoretical basis, and we need such theoretical basis. In their case, it was the conceptual metaphor theory and conceptual blending theory. I took a snapshot from one of the slides. I think it's really important in our field that we look for theoretical foundations for what we are doing concerning computational thinking education, and also maybe in relation to mathematics didactics theory. So this was a very interesting part of this seminar series, I would say. The third session was the presentation by Workasant and Rivero. And what I take from that and what I appreciated in that is a very strong connection made between computational thinking and data literacy. And they highlighted this notion of data moves, which was something like transforming and analyzing data through some concrete actions. And what I appreciate in that is that statistics definitely is a very suitable field to address computational thinking in the frame of math education. Also a field that's highly popular now. Celia already mentioned it during the first lecture, how COVID appears in data in media, through diagrams and statistical analysis. So definitely statistics is a hot topic. And next, the transformative character of computational thinking is very important. That was also highlighted in the first seminar, I would say. In the fourth session, it was Kronis Kynagos presenting his powerful idea of these half-baked micro-worlds or artifacts. And well, he presented baking digital models and games, the art of the half-baked artifacts. He presented Malt2 and Choico. And I really appreciate this view. And again, to position myself a little bit, I would like to make a plea for the three-quarter baked micro-worlds, in a sense that in the micro-worlds that we would use in math education, in the frame of computational thinking, I would like them to be very close to conventional mathematical expression. And that's why I moved from 1/2 to 3/4, just to express that we, in my opinion, should make sure that we stay close to the conventional mathematics, not because I'm old-fashioned, which I am, but that's not a topic here, but mainly because mathematical knowledge is, well, an important body of knowledge that we should do justice, and we should not, we should keep that in mind, in my opinion. So my apologies for skipping the fifth one, which I was unable to attend. To summarize my position, I focus in this talk on math education and not so much on coding and programming. I think I would like to try to integrate attention paid to computational thinking within the more conventional mathematics curricula, even if they are subject to changes, of course, and to use popular mathematical tooling. One argument to do so is also to convince teachers of the interest of doing so, and to avoid complaints about time constraints. This is interesting, but we cannot do it because we have to teach it the traditional math curriculum. If we connect the two more closely, this would be more attractive to teachers. And finally, I like to look for connections between math education theory and teaching computational thinking. So far more for then you have a brief impression of where I come from and where I want to go to. Now, how about computational thinking? A lot has been said about that already, so I will go through this a bit briefly, but clearly it is in the air. And in the meantime, it's a container concept. That it's in the air is also witnessed by the table at the right-hand side. It's a paper that appeared this month online, and it just shows you how many special issues in journals there already appeared on computational thinking. So it's really in the air, but what do we mean by it? Let's focus on the C. Does the C stand for the student who is able to compute? I don't think so. The student behaving like a computer? I don't think we really want to educate people to become like computers. The student should be able to work with a computer. That's at least true, but is it computational thinking? Maybe it's more that we want students or citizens, people, to be able to make a computer calculate, or at least to transform a problem in such a way that it can be solved through computation. And I guess it's the latter one that we at the moment mostly think of. How about the T? Well, of course, it stands for thinking, but I played around a little bit with the T. You can also think of transformation, computational transformation. Computational transposition is a terminology that was coined by Balachev already in '94. I will say a word about it in a minute. Transparency, because tools often are not so transparent, and part of the art of being able to make full use of them is making them more transparent for yourself as a user. So tool transparency is an important element in our discussion, I guess. On this computational transposition, this is a slide, an old text from Nicolas Balachev from '94, where he refers to designing symbolic representations of knowledge to be able to implement it on a computer-based device. So again, you have to transform your knowledge or your strategies into representations that other humans or devices can use in terms of computations. So in fact, what I find interesting, Balashev's notion is that already in 1994, he touches, in my opinion, the core parts of computational thinking. So it all started more recently out with this global definition by Jen Wing, which you all know, I guess. And this definition has had many follow-ups. For example, Fletcher here phrased the problem so that it can be solved in terms of computations, not necessarily carried out by a machine. This is a recent one, which I found in a 2020 paper in Olympiads in Informatics Journal. And what I liked in this Lodi paper is that he says, computational thinking represents the disciplinary way of thinking that exists within informatics. And computational problem solving refers to expressing the problem in a way that allows for external processing. So I think, in my opinion, there's a kind of convergence in thinking that goes into this direction. Here are some, other resources, the ISTE, which with some very interesting keywords like problem solving, data sets, algorithmic thinking, abstract models. This is CSTA and ISTE, formulating problems, analyzing data, algorithmic thinking. Well, many well-known terminology that we have seen around during these seminars, and that is my perspective, also make me think a lot about mathematical thinking. This is the famous Weintraub categorization. We see, for example, data practices being addressed in the second or third lecture. We didn't speak too much about modeling and simulation practices, I think. So, we can situate ourselves within this taxonomy. Here another few lists of aspects from other resources. And again, there are some commonalities: abstraction, generalization, decomposition, things that are quite familiar. Algorithms, the word that Celia just mentioned, because of the UK algorithm to decide whether students pass their A-level or not. Very interesting. And again, this Lodi 2020 paper identifies different aspects of definitions. Some definitions really focus on the mental and the thought processes. Other definitions focus on the methods that computer scientists use, like data collection, programming. Other definitions or aspects of definitions refer to practices that a computer scientist may use. And then there's a level of transversal higher order skills like design, create, reflect, be persistent, that are quite general and that you can also find in documents that promote historical thinking or mathematical thinking or whatever. I like this categorization because sometimes it seems to me that we mix up all these categories or these aspects, and that's not clarifying the discussion. To summarize, as you all know, computational thinking is rich, but also somewhat vague, somewhat container. But for this talk, it's important that it shares many common grounds with notions of mathematical thinking. So let's reflect a little bit on mathematical thinking and its relation to computational thinking. Well, mathematical thinking is very important. As Polja already said, the main goal of mathematics education is to make young people think and to go beyond routine procedural work and to deal with more sophisticated mathematical tools. So for these reasons, mathematical thinking, as in many other countries, has become a core goal in the Dutch mathematics education, both for upper secondary and also in the ongoing reform for 4 to 18 math education in the Netherlands. For example, here you see a slide from 2015 in which modeling, algorizing, if that's his English, I don't know, making algebra out of it, structuring, analytical thinking. So these like higher order mathematical thinking skills are coined as very important in the new math curricula in the Netherlands. More recently, last year, this is an image of which should outline curriculum reform in the Netherlands from 4 to 18. The dark blue dots are the more traditional mathematical content bullets, like data, statistics, geometry. But the light blue ones refer to more higher order thinking skills. And in particular, this one is about using tools and technology, which is now apparent, well, if everything goes well, which is a political issue at the moment in the Netherlands, which should underpin the curriculum reform in the Netherlands. So clearly, curriculum reform focuses on mathematical thinking, and to simplify things, I prefer to focus on problem solving, modeling, and abstraction. Well, because the previous lists were a bit too long. So to me, this is very core in mathematical thinking. And of course, this is not just happening in the Netherlands. For example, if you take United States Common Core standards, you see a lot of similar approaches and many other countries. So there seems to be quite shared intention to pay attention to mathematical thinking in mathematics education worldwide. So how does this relate to computational thinking? Well, if I take these mathematical thinking aspects on the left-hand side and some of the computational thinking literature aspects on the right-hand side, you clearly see a lot in common. Problem solving is mentioned on both sides, abstraction, generalization, decomposition is not explicitly mentioned, but sorting out, structuring could be considered as such. Algorithms are connected to formulas. Well, so very easily it becomes clear that there's a lot of potential intersections between mathematical and computational thinking, as was already expressed in the first talk by Nos and Hollis in this series. So what we want to do is we want to exploit these common grounds and make this happen through designing and implementing computational thinking aspects in mathematics lessons. And I will address these two parts in a bit more detail. To start with exploiting these common grounds, we did a literature-informed Delphi study, which is now under review. The paper reference you see below. And this Delphi study started with a literature study, quite well, traditional setup, I would say. We used many databases and a query, and we ended up with 56 papers that we found relevant, both empirical papers and more theoretical ones. And to give you a glimpse of what we found is that if we identify computational thinking aspects in this literature database of 56 papers, we see a lot of well-known terms coming up, with a slight difference between more empirically oriented papers and more theoretically oriented papers. But I would say the usual suspects, so to say: automation, abstraction, modeling, algorithmic thinking, decomposition. It's really, this is really what emerges if you look at the literature available at the moment. So no big surprise here. And we use this literature review study to feed our Delphi study. I'm not sure if you are very familiar with Delphi studies, but what you do is, with a small group, in this case 25 Dutch experts in the field, you interview them and you raise questions to them, and you do this in multiple rounds, in our case in 3 rounds, because the results of the first round are synthesized and form the input for the second round, and the third round. And in this way, you try to come up with some agreement among these 25, in this case, persons. So we raised 3 questions, which all 3 refer to the relationship between computational thinking and mathematical thinking and mathematics education. And again, well, on the one hand, I'm sorry to say, on the other hand, it's a nice result. The outcomes were not surprising at all. For example, if we think about the first question, computational thinking in mathematics education, and you ask the experts, where do you see the most fruitful chances or aspects that we might address, the list of terms that comes up is again very close to the previous list I showed you. So people say decomposition, like breaking down a big problem into small partial problems, is something that you could really do in mathematics education and includes a focus on computational thinking. Same for pattern recognition and the other things that you see there. So the expert we consulted really agreed upon the potential of these ideas to address computational thinking in the frame of mathematics education. Second question, common aspects of computational and mathematical thinking. Again, a lot of agreement. Of course, you don't see the items that people didn't agree upon, but in fact, this is an important subset of what we brought forward. And again, I'm not going to read them all, but you clearly see a lot of things in common with the lists that we saw previously, which is again not a surprise, but on the other hand, good news, because it clearly shows that there are some opportunities, there is a lot of potential. And the same essentially for the third question, what do you find feasible to address in math education, in math instruction, related to computational thinking? And again, the same key, well, not exactly the same, but similar lists of key terms come up. Of course, it is a question if a mathematician means the same when he speaks about abstraction as a computer scientist when he or she speaks about abstraction. So this is just very superficial key terms. As a next step, we should dive into it and see what it means, and if we have common grounds there as well. But for the moment, roughly speaking, we conclude that if we think about computational thinking, we think about a structured problem-solving approach in which we rephrase, reformulate, and solve a mathematical problem in a way that other people or a machine can carry it out by employing, and then we get these keywords like abstraction, decomposition, pattern recognition, etc. So roughly speaking, this is where we are from our theoretical point of view. We see many aspects, which is the second part of this long phrase, that could be addressed within math education, and in the meantime, foster computational thinking. And this is what we are trying to do now. Okay, so far. So problem solving is a fundamental goal, and we want to address rephrasing the solution in such a way that it can be transferred. So now we set the scene, but what does it mean for teaching practice, for reality in the classroom? And this is where design comes in. We started a design study for 11th grade, means students 17-year-olds, maybe some 16, some 18. Most of them are 17-year-olds. And in the Netherlands, we have two mathematics subjects for this age level, namely called Math A and Math B. And Math A is more focused on application of mathematics, for example, in social science. This is for the future student in psychology, medicine, law. And we have a more pure math curriculum, Math B, which is more for the future student in physics or mathematics or chemistry or biology maybe. So that's the more pure and more abstract subject that we have. And because these two courses are quite different, we set out to design two lesson series. And we have some guiding principles. We wanted to co-design these lesson series with teachers, which is what we did. And of course, the activity should address both mathematical and computational thinking. We focus on problem solving, on data representation, and on algorithmic thinking. And these choices are guided by the curricula, because like I said, we want to address topics that are core in the existing math curricula, not in the least because we want to convince teachers to take part in it. Fourth point, we want to make students use digital tools that are relevant for mathematics and are popular and used frequently. And we integrate plugged and unplugged activities, even if the focus of my talk today is more on the plugged ones. So how did this turn out? For the Math A curriculum, we decided to focus on statistics. I already mentioned the topic. It's a core topic in Math A curriculum, but it's also very important to all citizens and future students and future professionals. We focus on data representation and data structures. Think about the data moves that were mentioned earlier. And as digital technology, we made this, not very spectacular choice for Excel because it's accessible, it's used very frequently. Mathematics teachers like to use it. We thought of using R or more advanced tools, but in the end, at the moment, we focus on Excel, even if we also provide versions of the teaching sequence for other tools. For the more pure mathematics, we focus on algebra and calculus and functions in particular, which is very core. And we focus on algorithmic thinking and problem solving because we saw some very nice opportunities to connect to the curriculum and to address computational thinking in the meantime. As digital technology, we use GeoGebra, which is very popular in the Netherlands. So students might have used it already before. And also now that GeoGebra has a CAS engine, computer algebra system embedded, it's really a wide range tool to use for mathematics. So now I zoom in on Math A first and then in a bit more detail on Math B. For Math A, focus on statistics, we use Excel, and we present a student with a kind of problem-solving cycle, which is very close to the traditional modeling cycle that you all know, I guess. And we use Excel for the students as a tool in different phases of them going through this problem-solving cycle. And students need to manipulate, move the data, so to say. They sort them, they select them, they recode, they aggregate, they enter Boolean functions to find things out. So they really engage in data manipulation and a little bit in algorithmic thinking in the sense that they use some algorithms and have to code them like for example count if commands in Excel, and to evaluate some algorithm results, for example regression. Now to give you a snapshot, we use two types of problems. One is the Titanic data set. You remember there were a lot of data on the passengers who were on the Titanic when it's during the catastrophe. And there's some interesting data analysis to be done there. For example, this adagium of women and children first, did it really happen or not? So we make students explore that. And the second data set is on school grades and relationships between different variables in that. Again, this is not spectacular in a sense of a revolution, but we do feel that we have the opportunity to exploit the possibilities, the affordances of the tools and this problem situation to, in a very gentle way, try to address computational thinking in the mathematics lessons. Here you see some snapshots of the worksheets that students are working on. There is some, some recalculations done. There's a logical test done. Because if you want to know if somebody is a child, you have to do some calculation on the age of the passengers. So there's some work done here. And like I said before at the start, unfortunately, students worked on this teaching sequence only in distant education, and we didn't have the data that we would like to have. So I'm not able to really present you nice data here. The regression analysis, some R-squared calculation, which students have to make sense of. So this is the type of work we want students to do in the second part on the student grade dataset. So far the snapshot for Math A. For Math B, we want students to consider functions as objects through using parameters, through making use of functional definitions in GeoGebra, and through merging steps, collapsing multiple steps into macros. We also want them to engage in conditional reasoning through if commands, Boolean reasoning, so to say, repetition and iteration. And in what I want to show you now, the focus is on object formation. And please allow me to make a short sidestep to mathematics didactic theory, because I said I want to try to connect the two. And object formation, of course, has been an important topic in abstraction. Because abstraction, of course, is one of the things that was mentioned many times in the intersection between computational and mathematical thinking. But we also know it's very hard. It's a barrier to many students. And I would like to focus a bit on that. And my ambition, of course, is to enhance abstraction in mathematics teaching. And there's a lot of theory about that. And some of the theories focus on object formation. For example, here you see a slide in Dutch, but you might recognize it a little bit. Young kids, when they have these candies like Smarties, when you count them, they count on their fingers. And the number 5 is a process of 1, 2, 3, 4, 5. But at some point, 5 or 32 becomes an object in itself, which you can use to add another number, 32 plus 7. Or you can compare different numbers and you can establish relationships. And maybe at some point you want to speak about numbers in general and you speak about variables. And these variables are building blocks for functions, which you can write down in different ways, like x arrow x squared, which is a very operational notation, or you can enter equations and like Pythagorean theory. So what you see in mathematics education and in mathematics in general many times is that processes turn into objects. And this is where Anna Svart wrote his seminal paper upon in 1991 already on the dual nature of mathematical conceptions, because conceptions have this process aspect or phase structural, and a more, process, dynamical, operational, and a more structural character of objects. So reification, the process of, well, bluntly speaking, turning processes into objects, is important in abstraction. And this is what I want to focus on. And of course, we have Gray and Toll in the same periods. That's why I have this roaring 90s icon at the top right of these slides. In fact, Gray and Toll, this procept idea is quite similar. Objects or procepts, in fact, the word procept is maybe not ideal, but processes and objects merge into mathematical conceptions. And we have this APOS theory, Dubinsky and Cottrell, in which they sketch this process of encapsulation. Now, if we want to focus on abstraction and object formation in mathematics education, which we want, and if we want to pay attention to computational thinking, which we want, and if we want to use digital technology, which we want, can we do so through focusing on what I call functional algorithms, namely engage students into using GeoGebra in this case to express themselves and to make GeoGebra do a lot of mathematics for them because they rephrased it, they coded it in a language that GeoGebra understands. And this is what this teaching sequence is about. And I will show you some examples to become a bit more concrete maybe. And I'm going just to show you the snapshots and not going to do it real life here. What we ask students here is artificial because GeoGebra already offers an option to draw perpendicular bisectors in geometry. But we are now in algebra and calculus, so we ask our students, could you reconstruct or recode this procedure in GeoGebra using algebra? So what they do is they have 2 points. They define the midpoint in the 1, 2, 3, 4th line. And then they define a very general equation of this perpendicular bisector. And this is high-level reification, I would say, because they condense this procedure of defining a perpendicular bisector into a quite abstract language which GeoGebra understands. So this is computational transposition or transformation, I would say. And the reward, like in the case of programming or coding in Scratch, is that you get the picture as GeoGebra would have it. So we are like mimicking GeoGebra through algebra in this case. And the final line, because this procedure doesn't work if the line is vertical, so there's an exception there to solve, and this is the Boolean in the final line. So what we try to make our students do is to reconstruct something that exists already, but it's quite rewarding if you see that it works. And the language is mathematical language. So this is the starting point. Again, I just show you some snapshots. This is the next phase. You see a parabola and a tangent line. But the interesting thing here is twofold. First is that in the bottom line, you see the expression raaklijn, which means tangent line in Dutch. And the students are invited to set up a very general tangent equation. You see f prime of 1. So f prime is the derivative of f for x equals to 1 times x minus 1 plus the function value. And this is already a relatively general definition because the function f is defined including parameters a, b, and c. So if I will move the slider bar, the parabola will change and the tangent line will change accordingly. It will remain the tangent line to the new parabola for x equals 1. So this is a certain level of generalization and abstraction and object formation because the tangent line now is not something you calculate or you draw. It's not an action. It's an object which you make, which can be subject to changes of the parabola. So there are some like higher order processes that you make act upon this definition of tangent line. And this is what Swart already mentioned in 91. Reification and object formation is accomplished also through establishing higher level actions on these objects. So I see a clear link between computational thinking, mathematical thinking, and abstraction in terms of reification. I hope you are still with me. A third example, here I use also the CAS engine of GeoGebra. It's nice. When I was a boy, I was bored in school often, and I took a triangle and I started drawing these lines, straight segments, to create some curves. This was when I was like 11-year old, and now I do the same, but now using GeoGebra and a bit quicker. So I hope students will get fascinated if they can make these type of pictures and graphs. You don't draw a parabola, you just draw straight lines, but the result looks like a parabola. That's interesting. And how do you do this? Well, in the mid-screen, you can see I define in expression 3, I define the derivative in a generic way. And I again define the tangent line in a generic way. And in the left screen, you see on the 5th line, maybe, a sequence procedure. So, and the subject of the sequence procedure is the tangent procedure. So again, you see this layers of objects and processes, which I hope enhances this abstraction and reification process, which is also an aspect of computational thinking. So what I hope, and like I said, unfortunately, I don't have evidence from student data yet. What I hope in this way is to engage students into this process of reification, abstraction, through expressing themselves through mathematical language to GeoGebra. Finally, the 4th one is a very generic one because all I did is I changed in the mid-top line, I changed the function. And because all my definitions were generic, the rest changes immediately with it. So I get a sheaf of graphs which shows this graph of the square root function rather than a parabola. So I built a very generic engine to create these useless pictures, useless but still nice. And I'm happy, I find it rewarding because I was able to make GeoGebra do what I have in my mathematical mind. Then this comes close to what I think already in the 95 book by Nelson Hoyt were called expressive tools. So in conclusion, I try to show you that from a literature study and a Delphi study, we see quite a lot of convergence towards what computational thinking is, how we understand it, and this clearly coincides with the previous lectures in this series, and that there's a lot in common with mathematical thinking. And the Delphi study also shows a lot of agreement amongst experts. In the meantime, my position is that we design and pilot activities that exploit the means to address computational thinking aspects in the mathematics classroom in relatively traditional mathematical topics, and using relatively traditional mathematical tools, digital tools like Excel and GeoGebra. So far for the good news, still we are a bit puzzled in this ongoing project. On the one hand, because tool use, well, on the one hand, you know this all by experience, the tool may absorb student attention very much. And of course, in GeoGebra, for example, the mathematics is always there, but there is a tendency for some students that ways in finding out how to use the tool may sometimes hinder the mathematical thinking. And this is where this famous instrumentation idea comes up, or as Sia mentioned, the tools are shape the students' thinking and are shaped by the students' thinking. It's still a challenge to make sure that students, when they use these tools, don't forget to think mathematically. The other thing which we struggle with is the relationship between tool use and coding and the unplugged algorithm experience. For these 17-year-old students that we target now, we find it still a bit complicated to find real nice unplugged activities, and I really look forward to your input on that in the discussion. Because this was more or less my final slide, I would really like to thank you for your attention. And also, I would like to thank the Dutch organization who granted the project, and my two colleagues, Sylvia and Maria, who contributed to this talk. Thank you very much.
Thank you so much, Paul, for your talk. For me, a lot of fresh ideas in that I haven't spent a lot of time looking at Excel or GeoGebra and as a tool. And your last few comments about the nature of the tasks, I think, raises the question: how do we design tasks so that these tools become useful and become interesting enough and capture students' attention? So I think that's at the heart of it. And looking at the pictures we saw, I think those would grab student attention. And then the challenge is then, I think that you raised was, how do you do it in such a way so that the in-between process from getting from nowhere to somewhere, that it doesn't meander in different ways that are not productive. So a lot of interesting ideas, I think, presented, and you also took us through a journey of what is computational thinking and how it relates to mathematical thinking and theories around that. So thank you so much for that. So it's time now to open it up for discussion. I will have a question for you, I hope, at the end if there's time. But first we'll ask if there's anyone on our panel that will have any comments or questions. Celia?
Oh no. Anyway, thank you very much indeed. And I really appreciate the talk, Paul. Thank you. And I think many will appreciate your very careful bringing together of all the different papers that are now coming out on computational thinking. When we first used the term in Scratch Maths, I don't know, about 5 years ago, there weren't so many things to read. And now it's an explosion. And I think your synthesis is extremely helpful. And I mean, this is because you don't have your student data, just from being engaged in your project. Can you just say what you think this focus on computational thinking in mathematics teaching and learning, what did it seem to offer the teaching and learning process? I mean, I know you haven't got the data, but what did struck you as something, because the examples you gave were lovely, but you're looking at them with a new lens. They're not new examples, but I just wondered what struck you about this new lens. What did it leave you with, just as an impression?
Yep. Thank you for your compliments and for your questions, Celia. But first of all, you're completely right that many of the things that we are doing now and many of the things that I presented today are not completely new. So from that perspective, it might be not so very revolutionary compared to some other activities. On the other hand, in my opinion, these traditional things, well, relatively traditional things, we did not manage so far to really implement and make them a success. So I'm using, in fact, the opportunity to see if we can make a success out of the things that we already knew 15 years ago. So this is not just an introduction. As an answer to your question, to be honest, we were, due to this COVID situation, I didn't see much of the students' reactions really, because schools were so much struggling with getting organized. And so most of the things we saw were written work by students or interview data by students, and not students really at work. That was very limited. What I think also from other experiences is might do the job is at the end a kind of fascination that students, and I think that's quite similar to your experience in Scratch and in coding, the reward of seeing that something happens as you intended it to happen, that you created something that works on your screen. And if it's a Scratch effect or a turtle diagram, or if it's a sheaf of graphs, that's not the main difference. So I think we should really engage. What I hope that will work is that students' engagement raises because they see that they create something and that they are productive. And this is why I said programming and coding is a means, because the main thing to me is the feeling that you're productive, that you created something, that you are in the lead together in cooperation with the tools you use. And I've seen my impression is that students are sensible to this. At least I should make a kind of remark. These were 17-year-olds and also relatively high achieving. They were pre-university. They were not the top 5%, but they were the top 20% of the student population that we have in secondary. So I'm not sure about the generalization of this to other levels. But the brief answer is engagement because they create, they are in the lead, they are in control. And sometimes frustration if it doesn't.
Thank you.
Thank you, Celia and Paul. Anyone else? Richard?
Thanks, Paul, for your talk. And thank goodness we have this technology, actually. Otherwise, none of us would see each other from one year to the next. But well done. I have a slightly, I don't know, I hope this doesn't come out as a grumpy question. But you said, and I say it as well, but sometimes I wonder what I mean by it. You said, we're trying to develop a theoretical framework. And supposing we couldn't, or supposing we didn't put enough effort into doing that, what would we really lose? Is that really the number one objective? You've got some lovely activities, you know where they're going, the students did the best they could in difficult circumstances. And I just want to know, from your point of view, what would the difference be, supposing we had a beautifully fully fledged theoretical framework to insert the work in?
Okay, well, thanks for this grumpy question, Richard. No, really. So, well, it seems as if you're asking, what do we need theory for? And that's, of course, a nice question. But what I always say to students is, and to PhDs, is we don't work for theory, theory works for us. No. So theory should work for us in a sense that if we have these insights, for example, like Schwartz's paper in '91 on object formation and on the duality between processes and actions and concepts and structure. To me, and this is personal, to me, this theory works in the sense that it helps me to better understand what students do, what they can do, what they struggle with, and to better react to their needs, respond to their needs. So in that sense, theory works for us. And I believe the same holds for our debate, our work on computational thinking. It's relatively new. Everything we do is relatively new. So I think it's really helpful if we have some shared vocabulary, some shared knowledge, which helps us as researchers, but also as teacher educators and as teachers to better, interpret what we see happening with our beautiful task and our beautiful tools. Does that answer your point?
Yeah,
or not?
That did it.
Yeah, thank you.
Thank you, Richard and Paul. Paul, your earlier comment about students and what they like about it, that they're in charge and they're creating something, I think you said. And it reminds me of, the goals of Papert,
Exactly.
who's in charge and get them to create something. And that's how you create a logo. Here you are. What are you going to do? There's nothing here and you're in charge. create something. So interesting that it just takes us back to, his ideas. You're kind of that.
Definitely, definitely. So constructionism is not far away at all. So the only, maybe what's a slight difference, which I maybe highlighted a bit in this talk for the sake of diversity and discussion. What I do prefer is to mobilize this, to engage this, to make this happen, but maybe also to convince teachers and to make it happen in everyday classrooms, to make this come a bit closer to regular mathematical topics and tools. And that's probably a difference, a slightly different approach.
Thank you. So I do have more questions, but I see Krista's hand up. Krista?
I would like to thank you very much for this presentation. I'm going to put it in a resource for a course that's starting next week in our STEM education, where they have to learn how to develop tasks or design tasks with computational thinking and mathematics. One of the things I lack is secondary applications. And so this is really lovely that there's a nice secondary resource. And you were talking about unplugged activities. One of the things I used to do is have nails in a square around a board, and I'd make these string diagrams, and they were always parabolas. And I never made the connections between those parabolas being, the lines being tangential to the parabola. So that would have been a nice link. And I am going to go into GeoGebra and make some of those string diagrams with tools. So thank you very much. I really appreciated your careful delineation of the definitions and how you separated them out and compared them to mathematics. That's very useful for me.
Thank you very much.
Thank you, Krista. Anyone else on the panel? We can open it up to all attendees. I don't see any questions in the chat at the moment. If you raise your hand, then I can turn your mic on. Oh, there we go. Joyce. Joyce, give me a second. Okay, Joyce, please go ahead.
Can you hear me?
Yes.
Okay. Well, thank you so much again, Paul, for your presentation. And I remember meeting with you at SEMI at Utrecht, and you were starting talking about computational thinking by then. I just have one follow-up question from that conference, and then another one. One is, you just started talking about the embodied kind of cognition or embodiment. I'm wondering if you are continuing to think about that in this research as well that you are involved in. And then the second question, I just saw when you were talking about these aspects of computational thinking, it was tinkering. Tinkering was right at the end, and it's almost again disappeared, I guess, when you were doing on your study. And yet I think, isn't that a big aspect, I would think, of computational thinking, this idea of tinkering and experimentation? So I was wondering about your comment on that.
Thank you, Joyce. Of course, I remember our talks in Utrecht. Embodiment is still, indeed, in our group, we do a lot of work on embodiment and digital tools. Even if this is in different projects, between the project, there's not a lot of relationship, but clearly, in fact, for example, last week we had a PhD defense on research onto young students, like 10-year-old kids who were exploring motion distance graphs through a motion sensor. Bluntly speaking, it was a bit more detailed. We also have this example that we presented a few times already on having your fingers moving over the unit circle and the trig graph. So in fact, this digital tool use for embodied experiences is a really powerful idea, I believe. Sorry, there was some sound somewhere. We did not yet connect the two clearly, to be honest. It would be very interesting to look for more embodied ways to express yourself in this digital environment and to make things happen that you wanted to do. So I really believe that's a very interesting point. It was not yet in the focus of our project, unfortunately. Mm-hmm. And your second point of the tinkering, yes, definitely. This is what you are doing when you're using scratch paper, but also when you are using digital tools often, I guess. If I would have had student results, I think I would clearly be able to show you this process of tinkering. At the moment, I just showed you some nice ideal student possible outcomes, but definitely this idea of tinkering makes completely sense to me.
Thank you.
George, you are muted.
Thank you, Chantal. Thank you so much, Joyce. Anyone else? Oh, Chantal, please.
Yes, may I? Paul, I'm going to go back to what I think George mentioned before when you said about when students are in control, when they create, about their engagement. And just recently, just analyzing a teacher behavior and comments, he's been mentioning about how we should let students in such contexts, when it's in the engagement, we should let students struggle, because if there's no struggle, there's no learning. And then he mentioned that it's actually a constant call of judgment from him to assess how much he should let the students and so on. Do you see that judgment call from the instructor being somehow different from a usual mathematical situation, a struggle on a math problem? Or do you see if it involves in a computational thinking activity in mathematics, if that judgment call requires something different? Is this a different situation? Mm-hmm. And then if you could as well, for the teacher, do you have any recommendation about how to handle such situations if that occurs?
Yep. Well, of course, interesting but difficult questions, Chantal. First of all, from a bit of a distance, this is quite general and has been there for centuries, namely that students doing mathematics experience success and frustration. And well, like in game theory, to be in the flow, there should be kind of a delicate balance between reward and success and frustration. And that's a very general thing also in mathematics lessons that every teacher knows and deals with. And dealing with these things, to me, in my my theoretical framework, if Richard doesn't blame me, from my lens, this is definitely instrumental orchestration. Like, how as a teacher do you set the scene with all the tools and resources available to engage students into the targeted learning? How do you set the scene? How do you exploit the scene? And how do you act ad hoc when all unexpected things happen? And in principle, there's not a big difference compared to traditional teaching. In reality, there is, because first of all, the setting gets more complex as soon as you have digital technology around. And second, it's teachers are not so skilled in it and have to get used to it. They have to develop their, what I would call, instrumental orchestrations. And that's why I found this paper by Anna Isabel and you yourself and some colleagues in the Constructionist Conference 2020 interesting, because it was about how a computer science teacher orchestrates the students' learning while students are programming. So I think there's a long way to go. The principle is not different. but the situation is on the one hand more complex and on the other hand more new to teachers. So there's a learning process and a professional development process needed there. Does that make sense to you?
Thank you,
Yes,
Chantal.
thank you.
Any other comments or questions? So I'll maybe there's a couple of minutes I could ask one question. I've been thinking when I worked with teachers or when I listened to presentations aimed at teachers, and I listen to people talk about computational thinking, often they also say something like coding and computational thinking. And I'm puzzled by that those two are together and what the difference is. But when I listen to them, I find that their descriptions, well, they describe what computational thinking is. And I'm just wondering if computational thinking may be leading us in practice, maybe, to descriptive ideas as opposed to ideas in action. So does it lead us to talk about what it is versus what it does? Not computational thinking necessarily what computational thinking does, but what the tool does, which is a computer, that they can be programmed in some way. So you've got something that can compute for you, and what does it do for you that's different, that you couldn't do without it? And I was wondering if it takes away from that, because I find if I talk about that, then I can engage teachers. I can say to them, here's what you can do with it. That's different. And here's what it looks like, and they get excited. But if I start defining computational thinking for them, it doesn't seem to help, because it overlaps with so many other things. Mathematical thinking, computational thinking, what's the difference? Yeah. So just a comment there, maybe from your experience in talking.
Yeah, well, I'm not sure if I fully understand you, but I do admit that I have a colleague who is professor in history education, and she wrote some nice text about historical thinking. And of course, the big game then is, what if I do search and replace historical by mathematical? And how does the text look? Mm-hmm. Not too bad, actually. Mm-hmm. So that's one thing. We have a lot in common, so we should be maybe a bit more specific and more precise. On the other hand, I'm not sure if I completely understood you, but if I start with teachers, well, if you speak to somebody, it's like the general educational principle, you better start bottom up and top down. So if I would speak to teachers, I would prefer not to start with abstract definitions of computational thinking, but by showing some examples and then see if they get engaged. And then at some point after, and of course, it's always difficult to know what's the right moment, but at some point you see, okay, this is the moment to generalize and to abstract a little bit and say what these examples have in common and what the underlying ideas or goals are. So to me, it sounds like the didactics of professional development. Does that make sense?
Mm-hmm. Yes, thank you. Any last comments? Let me scroll through our participants. So Chantal, it looks like we're right on time. So thank you so much, Paul, for your excellent talk and all the ideas you raised in the discussions we had. So I'll turn it over to Chantal.
Thank you.
Okay, so thank you, Dr. Paul Drijvers. What a great way to end the seminar series. That was a very, very nice way, I have to say. We will now be briefly closing the seminar series. So if you cannot stay, I would like to invite you to please take a minute to just fill out the attendance survey. You have the URL here. And I believe George will put it as well in the chat so that you can simply click on it to access it. So this is again an overview of the program. We want to thank all the speakers for the generosity of sharing with us their research, their understanding on the topic. I remind everyone that the seminar series aimed at providing a platform to discuss recent research on the integration and the use of programming and computational thinking more broadly, especially after Paul corrected this title of the seminar series, in mathematics programs. Our speakers indeed presented their research, and it addressed diverse topics, and such as student learning, the interplay between the affordances of computational thinking and mathematics. We just heard about the interplay between computational thinking and mathematical thinking, also addressing the nature of exemplary tasks, pedagogical models, online resources, and so on. So I'm gonna just go now with a brief overview, although Paul just gave us a bit of an overview of the talks. But before, I wish to thank also all the participants on the online series. As you can see, I mentioned before, we were more than 250 participants in total from the series from 30 different countries. And in addition to that, there's been, as of today, more than 300 views of the seminar recordings for the seminar series. So we have heard on June 19th, so for the opening, the launch of the seminar series, Celia Hose and Richard Nuss, who presented the design and the implementation of a nationwide program, Scratch Math. I don't think I need to name it anymore, but here I am, for the learning of computational thinking and in a mathematics context. So there was the learning both and computational thinking and mathematics, and that was for grade primary school, so grade 5, 6. On June 3rd, Krista Francis and Brent Davis discussed in details a video of 2 students and 1 teacher engaged in a robotics activity, and as to how this was supporting the students' conception of number, of development of their concept of number. On July 17, Michelle Wilkerson and Eduardo Rivero discussed data practices, so a different perspective, and how this could actually be integrated to involve socio-scientific issues such as nutrition, environmental racism. On July 31st, Konis Kinigos discussed about half-baked microworlds. In that case, where students use programming and math concepts, or with math concepts of math concepts, to develop computational thinking. 2 weeks ago, on July 14, Ricardo Scucuglia brought the idea of aesthetics and performance into this computational thinking for mathematics education. And today, Paul Drijvers nicely outlined, I would say, the how mathematical and computational thinking are interrelated, and in particular, how computational thinking can be related to math education goals and practices, how going towards what is already being done, and how computational thinking is part of it, can be integrated. This is a very short summary But of course, I invite every one of you, if you have missed any of the seminar, to please go to the website and view the recordings. And I want to thank again the speakers who kindly responded to our invitation to recommend and provide related materials for teachers for teaching and research papers, so complementary to their seminar talks that are on the website.
I wonder if you could spare me 30 seconds, Chantal, would that be all right?
Yes, please, Richard, go ahead.
I wasn't sure if I would manage to make this point if I let you carry on, so this is probably the wrong place. But I just wanted to say a big thank you to you and to George and to everybody who made it technically possible. You couldn't have known, presumably, when you started organizing this seminar, just how incredibly important in terms of the history of the world, human world anyway, this year would have been. And it's fantastic that it's bringing together so many people who are investigating just what it makes, what one learns to program a computer. So thank you very much to all of your team.
Thank you very much, Richard.
Oh, that was on behalf of Celia and me, by the way, together.
Thank you. Yes, on this, we're pleased to announce that we will have seminars, proceedings. Let me see, where am I? So these will be published by the Mathematics Knowledge Network and the Fields Institute for Research in Mathematical Sciences, and they will be then posted to the website. We will send an email through the mailing list to inform you when the proceeding can be found on the website. We are hopeful to follow up with this online seminar series in 2021 or in the near future. And again, we will be using the mailing list to inform you if or when the series will continue. We welcome your comments or suggestions through which you could share with us through the attendance survey, which I will give you the link again at the last slide. Throughout the online seminar series, we received numerous feedback from you from many different parts of the world. Here, I will read one from Canada: enjoying the breadth of mathematics research available, and so on. I think that echoes a little bit what Richard mentioned, is that it was actually really listened to, and it seems like also because they are accessible online on the website, that it could reach many people that are interested in this, different stakeholders in mathematics education and in different parts of the world. So in particular, we would like to thank you for expressing your appreciation of the seminar series, such as what from Richard and Celia.